So we're going to discuss radioactivity today. These are the equations we're going to use, not all of them. We're only interested in 2 of those equations. I teach it different ways. For this class, I'm only going to teach with equations 47 and 48, and we will get to it shortly. Radioactivity. What happens in the case of radioactivity with respect to, well, where does all the radiation come from? I'm going to draw an atom. You guys are familiar with simple atoms. The atoms are made up of protons and neutrons. This is the nucleus. Here's the nucleus of an atom. And we've got protons and neutrons. In the nucleus of an atom, neutrons. Around it, there are, well, electrons. 2 in the first shell. And then goes all the way around. There's 8 and 8, etc., etc. You learn all this in chemistry. Electrons. In the case of radioactive decay, it's the nucleus that decomposes. It's the particles here in the nucleus that decompose. The protons and the neutrons decompose. And what they do, they will emit 3 different kinds of emissions. One of them being alpha particle. An alpha particle. Using the Greek letter alpha. The other one is a beta particle. This is beta minus. The details of this are posted. I'm not going to go into any details. And the last one is actually a gamma ray. And it uses the symbol gamma, the Greek letter gamma, the gamma ray. So these 3 emissions, they come from the nucleus. Come from the nucleus. The outer electrons have nothing to do with radioactive decay, only from the nucleus itself. The details, I will leave that for you. Let's have a look here. I have here a text. Oh, this is I used to tutor grade 12 students in physics. This is one of their textbooks here in Hamilton. Let's see what it says here in this text. Beta decay, I'm not going to go into the details of this. But it says here it's a neutron that decomposes into a proton and an electron, and a proton decomposes into a neutron and an electron. That's not for us to go into any detail, but it comes from the nucleus. And there's another comment here that I really wanted to show you. Here it is. It says here, the nucleus of a radioactive atom emits radiation as it decomposes. So it all comes from the nucleus. So radioactivity is the decomposition of the nucleus, protons and neutrons. To put it simply, I just have a paper here with me. I have here, showing to you here, 2 kinds of items. You can see this, the greenish color. This is uranium glass. Do you know of it?
Yeah, it's uranium glass that they used in the 1950s, but they're unable to use it anymore because of its radioactive purposes.
Oh, really? Uh-oh.
Am I wrong?
I don't know, but I bought this recently. So.
Oh, really?
Yeah.
Maybe I'm wrong.
So I have uranium glass, and you can tell it by the greenish color. Almost, but just with the greenish color. Let's look over here. I guess I just put some white piece of paper underneath. I was going for a bike ride in the summertime. come across the flea market, they had a sign outside, and it says, uranium glass sold here. Oh, son of a gun. So in I went, thinking of this class, of this particular class, thinking of my physics classes when I do this particular demonstration for radioactivity. So here is a plate made out of uranium glass, and I brought a little cup as well. And you can see, how do I know it was uranium glass? Well, somebody wrote on there, it was Stahl 13D uranium glass, cost me about $10. I left this tag on here. I had a similar tag on that one, but I washed it away. So here we have two items here, and it's uranium glass. And what does uranium glass made of? What's actually in there? I don't know. Let's go look at the Inter-Google. So we're going to go to the Inter-Google and see what that has to tell us. Simply asking a question there in a moment. So ask a simple question, what is uranium glass made of? And there we go. Uranium glass is glass which had uranium, or has had uranium, usually in oxide diuranate form, added to glass mix before melting for coloration. That doesn't tell me too much. So let's see down here. Uranium glass, safe for drinking.
Is it banned? Is it banned?
Is it banned?
The last one.
All right, let's go with that. Is it banned? However, in the 1940s, it was banned as a glass constituent because uranium was used to make the atom bomb in the 1940s, and consequently, there were fears for the health of glass workers. During the 1950s, these restrictions were lifted. Hooray! That's the reason I'm able to buy them now. And companies now use uranium as a colorant. So there is an amount of uranium in here. It's about 2%, if I can find it here somewhere. So I'm going to have to move on, let you guys search for that. So it's generally 2% uranium. Okay, this is spent uranium. It's not like the full-blown uranium itself, but in order to give it some color. And then you notice here they sort of glow. They glow in the dark. But do they glow in the dark? Let's have another question up here. The reason I can tell this is uranium glass is because I did this. All right, so why does uranium glass glow under UV light? I'll put down a black light. Black light, ultraviolet light, they're one and the same thing. There it is. So uranium glass fluoresces under ultraviolet light because the UV excites the electrons above the ground state and gives off photons as the electrons transition back to the ground state. And here's a couple of glasses here glowing under UV light. So what I did, you guys in the chemistry class in the third room of E wing, there is a black light. So I took my little piece of the glass, uranium glass, and I brought it to the third floor of E wing, and let's see what I did. And there it is, under a black light. I did a little more. That's the plate. Here's the glass. And this glass is exceptional under a black light. Look at the details on that one. I didn't know you had a black light in your chem labs. Another one down here, no. So the best way to find out if this really is uranium glass is to put it under a black light. And if it glows, as you see right there, you know you have uranium glass. Is it radioactive? Well, the answer is yes, it's radioactive. Let's find out. I got here a little wand. Gonna measure some things. Let's see if we get a reading here for radioactivity. It's not high enough. There is always a little bit of radiation. It's called background radiation. No matter where you are, you're always going to encounter some background radiation. This obviously has a little bit. Oh, sensitive. You guys heard of carbon-14? Carbon-14 is a radioactive form of carbon-12. It also acts like carbon-12. It's in all organic materials. That's the reason we're able to do radioactive dating, radiocarbon dating it's called. I got here an apple. And let's see I'm gonna put this thing on sensitive. So carbon-14 is radioactive. I am slightly radioactive. All of us have carbon in us. Well, you got carbon-12, and every once in a while there is a carbon-14 atom. It behaves just like a carbon-12 atom. As a result, carbon-14, because we eat organic materials, it comes in us, and we can be carbon dated. That's the reason they're able to do radiocarbon dating. I will talk more about that one in one of my examples. Good stuff. As I said before in the past, what I tell you is true, but it's not complete. So I'm going to complete this little story demonstration that I'm doing for you here. You got me? Here. I'm going to complete this little demonstration. This is not a Geiger counter. I cannot detect radioactivity with this. What it is, it's a metal detector. What I did, when you guys were looking up there, is I put some coins in here, such that it beeps. Now, beep on the coin, but it's not a Geiger counter, so it's not going to detect anything here. Oh. Well, I fooled you that one too. I embedded a loonie in that one. Maybe I'll put it here in class, such that I get a beep. I don't have the money to order a Geiger counter sensitive enough to pick up this background radiation, but it's a good demonstration for our purposes right here. Like I said, everything what I teach you here is true, it's accurate, it's just not complete, except now with my little magician's trick. Yeah, come on. I'm good at this. Yes, that was a good one. I got you all. And yes, this is uranium glass, as you saw. However, so radioactive materials, the way to determine what happens with them is that, or radioactivity within them is a thing called radioactive or half-life. I'm going to do a demonstration for half-life. What does half-life mean? Anybody know what half-life means?
So isotopes decay over amount of time, so the half-life would be half the amount of time that it would take for it to decay.
Okay, it's half the amount within the time.
Yeah.
She's got it right. Yes, it's half that's left over. Okay,
Yeah, that's what I meant.
radioactive
Like,
materials, yes.
there's
that's
an
good.
extended amount of time that
That's right, 1, 2, 3,
it can live for, and then that half of that.
7. I'm just putting in some dimes in my little radioactive cup. Give a demonstration of half-life. I'll go over here. Now dimes, coins, they have heads and tails. So the 50-50 chance. If I toss these, and then I'm going to get a head or a tail. And that's perfect for my demonstration. I'm just going to shuffle these a little bit. So in here are 12 coins. I'm going to count to 5. Count 5.
1, 2, 3, 4.
Shuffle the other around here, let's go down. So all of those that came up heads, okay, in the beginning, let me back up, in the beginning, when everything was in here, we'll say all of these coins were radioactive, every one of them, they all had some radioactivity, so they're all radioactive. After a length of time, any one of these, nobody knows which one it will be, one of these will emit a gamma particle, alpha particle, it will decay at any given time. So let's go, for our purposes, I'm going to take out all the heads. I'm going to say that all the ones that are heads, they have decayed and they're no longer radioactive. So that one's no longer radioactive, that one, that one, that one, that one, and that one, and this one. What do I have here? Head. Well, this one is really, a lot of them decayed on this one, so it's not going to be a quick demonstration, but nevertheless, here we go. Within that time, all of these here have decayed. These are still radioactive. Normally it should be half the amount, but in my case it's kind of be a little bit more, but that's okay. So that was in 5 seconds. 5 seconds, all of those have decayed, and now they're no longer radioactive. These ones still are, so I'm going to put these back in. It's a demonstration for a half-life. Put these back in. Give them a shake, 5 seconds. Keep counting. 1, 2, 3, 4, 5. Shuffle them down. And all of those that are top or heads will have decayed. That one and this one. So that's half of them. So half of the amount has decayed, so that's another 5 seconds. And 2 are still radioactive. No one really knows when an atom is going to decay. As a result, they work on probabilities and determine half-life. So 2 are left over, which are still radioactive. Let me go shuffle 5 seconds. 1, 2, 3, 4, 5. Come down. After 5 seconds, well, this one is the head. It goes up, and 1 is left over. So another 5 seconds. 1 is still radioactive. And after a period of time, this one here will also decay. But nobody knows when it's going to happen. It just does. And it's still a tail. Yeah, going by here. Eventually it's going to come back to head. There we go. One thing's on. So another 5 seconds. So in the case of this one right here, the half-life is 5 seconds. Half-life equals. So every 5 seconds, half of these coins will have decayed, and half are still left over, which are radioactive. Another 5 seconds, the other half of which are radioactive are now decayed. Half of them will have decayed, and half will be left over. Another 5 seconds, the same thing, until eventually there is nothing left over, which is radioactive. That's the term for half-life.